Okay, let me know when you can see it. Okay, great. I'm gonna make the, yeah, great. So good afternoon, everyone. I first want to thank you all for being here, both the ones watching it online and the ones that are watching it recorded after some months. So the name of this talk is Atomistic Internet of Things Penetration Testing Methodology. It is an entry-level talk, so hopefully everyone will be able to understand it and the approach that is suggested. And it covers the thought process that I followed when creating this IoT pen testing methodology that I've made for my current employer. During this presentation, I will try to answer the questions on why an IoT penetration testing methodology is necessary, and why, surprisingly, it is not as hard to apply as one would think of. Okay, the word atomistic here is really important because one of the conclusions that will arrive at the end of this talk is that when doing a pen test to an IoT device, it is better to see it as a pen test of many things, hence atomistic, instead of seeing it as a whole. Okay. Before we begin with the content, I'd like to introduce myself. I'm a telecommunications engineer and hold several pen testing and cloud security certifications. My interests at the moment are in IoT, of course, and web security. Also, I'm looking into the ways to add security into the DevOps model, and I also play CTFs in my free time, and I'm getting started in the book bounty scene. I was born in Girona, here in Catalonia, in a city up north, and I'm based in Barcelona since I started my studies. I love music in all its forms. I'm singing, guitar, cello, and I also do Krav Maga, which is the self-defense Israeli system. So really into the offensive and defensive stuff. So let's jump to the talk. Why this talk? Okay. My current employer is a company from the beverage industry, and it has factories across Europe. Okay. One of the things that we were worried about were all these small IoT devices that were being introduced into the factories, from which security documentation was rare and which we didn't know how to test. Okay. These recent years, we have seen several different types of breaches, from heart implants, as you can see in the screen, to defibrillators, to well, I think most of the security professionals have seen the funny car hacking videos that have been released these last years. But there was one specific incident which got a lot of attention, which was the Mercado data breach. In this data breach, what happened is that the access to an administration interface was lost, so credentials were reused, and the hackers got access to more than 150,000 like webcams. The image you can see in the left bottom of the screen, it's the Mercado camera in the Madison County Jail, where you can see the inmates doing their daily things. So the question that was made from upper management, and that is a recurrent thing. So when there is the supply chain attack, the Kaseya supply chain attack that was so famous so months ago, they also asked, like, what can we do to stop this? In this case, they asked, how can we protect these IoT devices that are being introduced? And we have to take into account that when talking about IoT devices, we're not only talking about information security. So we're not only trying to protect information that we store in our systems. More and more, we see IoT devices that are used by people, like, I don't know, these automatic drones or vehicles that have some autonomy, but are still manipulated by humans. In the event that these vehicles are hacked, as with car hacking, for example, so the consequences are really, really huge. Okay. And the first question that we had is there a bulletproof solution? So is there something we can do that will make IoT devices secure? So definitely not. But there are things that can be done. Okay. And before starting with the pen test methodology per se, I wanted to explain some of the things that we are doing and that I think that companies should consider. The first one that is usually done using under the GDPR is the third-party security assessments, where we check the controls that the suppliers have. And if you are a company who develops or who has other companies that develop IoT devices for them, then it's also worth it to have an IoT security standard and enforce it. Moreover, the biggest cloud competitors, these are AWS, Azure and Google Cloud Platform, have lately also released specific IoT management solutions. Essentially, what these solutions do is they allow you to onboard and offboard IoT devices, which gives you visibility on them. You can see, yes, if they have, for example, they also do like kind of an IDS, IPS function. So you can see if the device has open ports, if the device has no vulnerability. And also if it detects that one day, for example, IoT device starts communicating with a command and control, they can alert you of that incident, and you can respond appropriately. The last item that can be done is pentest IoT devices for low-hanging fruits. And the low-hanging fruits part here is really relevant, because we're not trying to use, I know that is a technique, and it's a totally valid technique for researchers who try to find very specific vulnerabilities in commercial IoT devices, but we're not trying to use lasers to modify the state of the chip and do things which are, I think, very hard for the majority of us to understand in a 45-minute talk. We're talking about mitigating the risk that the OWASP Internet of Things Top 10 has classified as the ones to avoid at all cost. And which are these IoT risks? Okay, and we have the OWASP Top 10 here. For those that didn't know, OWASP has a top 10 only for IoT vulnerabilities. And this top 10 is intended for both researchers, enterprises, and security professionals, and is labeled as the vulnerabilities to avoid at all cost. One could think that these vulnerabilities are really specific and really hard to exploit, but if you start reviewing the list, and we're going to do it really fast, but I think it's important to have this information for the rest of the talk. We see that the first one is weak, guessable, or hard-coded passwords. So yes, a web page where you can log in with admin and 1, 2, 3, 4. That was the usual thing in routers up until not so long ago. But nowadays we are seeing these Mirai botnets, which what they do is they hack IoT devices using default credentials, and they pick this huge botnet that can attack web pages across the world. Also, we have number 2, insecure network services. So again, and this is related with the lack of secure update mechanisms. So usually you have insecure network services because the IoT devices are not properly maintained. And what this means is having an SSH service that is outdated, an FTP server that can be accessed from the outside. Number 3 is insecure ecosystem interfaces. That means web pages, APIs, cloud or mobile applications which are poorly made and introduce new vulnerabilities to the IoT ecosystem. Then you have the lack of secure update mechanism, because one of the things that is really problematic with IoT devices is that you can plug a USB, flash a new version of the firmware that the IoT is using, and if the IoT doesn't have measures to control that, well, signature verification measures to make sure that the firmware that you're trying to flash is actually intended for that device, then you're going to be able to, I don't know, have a shell on the device, have an endpoint that's always listening for your commands, whatever you want. And the rest, it's a similar idea, okay? But insecure or outdated components, of course, if you can't update the device in a proper manner, you will usually have insecure and outdated components. Insufficient privacy protection is related also with number 9, which is insecure default settings. So we see a lot of things which are not vulnerabilities per se, but design faults that are there because no one has actually made a risk assessment of the IoT device. And well, then the lack of encryption, number 7, lack of device management, and lack of physical hardening. Okay, these are the 10 vulnerabilities to avoid at all cost. But before we start talking about how to address all these vulnerabilities with pentest methodology, I wanted to like waste 2 minutes to also show some of the documents which are really relevant, and for companies that are starting to look into IoT security, they can be interesting. ENISA has a super interesting documentation. They have 6 pieces of information, which start with a baseline security for IoT, and then they have the smart cars, hospitals, airports, cities, and Industry 4.0. So what they do, and here, for example, I have the part of the smart cars, is they do a document that first has an overview of the sector, then the assets that apply to this sector. Then they do a threat and risk analysis. So where are the weak points of this specific sector? And they analyze attacks as they have happened in the recent years. Lastly, they suggest security good practices and recommendations to avoid these types of attacks. The last document that I wanted to show is the IoT security verification standard. For those of you who come from an application security background, you are probably, so you probably know the application security verification standard from OWASP, which essentially classifies web pages in 3 different levels and then suggests us so requirements to make them secure. This ISBS document follows the same approach. What it does is it classifies IoT systems in 3 levels, depending on the type of data they are treating or the place in the factory that they are working, and then divide the IoT per se in 5 different sections. This is similar to the division, to the atomistic part that we're going to do for this pentest methodology. And essentially, you can see that these 5 sections are the IoT ecosystem, essentially web pages, APIs, and cloud platforms. Then you have the user space where you'll save the credentials and you encrypt the data. And then you have the communication part, which essentially will be the wireless communications, and the hardware platform, which means the chips that you have physically in that platform. So with IoT devices being added to the infrastructure, there was the need to first understand which was the attack surface of an IoT device, and then develop the pentest methodology that would help us actually protect these IoT devices by finding low-hanging vulnerabilities, okay? So I did what everyone would do. I went to Google and started searching which were the files, the articles that were more relevant and that provided more information on this topic. There was one mind map, which was really interesting, by Chirag Jariwala, they have here. And essentially, he devised the attack surface of an IoT in 3 different parts: hardware, software, and network. What is interesting about this mind map is that you can see which are some of the most used tools when attacking these IoT devices. For example, when you have a hardware part of an IoT device that you want to pentest, you can do glitching attacks, high channel attacks, but you can also try to connect directly to the exposed debugging interfaces like URT, SPI, I2C, and JTAG. The same happens with software. So you have mobile applications, web applications, okay? So this idea that keeps repeating. And then you have the network part with the different wireless protocols, but also the wired ones. The approach that Chirag followed to do this mind map is very similar to the one that I later followed, with the difference that when thinking it and saying, okay, how do I explain this in a easy to understand way? Because of course we have to speak with people across the company to ask them to do IoT pen test. How do I explain the different parts that we're going to test? And that led me to the following question. And the question is, what is actually IoT cybersecurity? And this is a very broad question, but if you think about it, so an IoT can have the cloud, it can have the web and API, it can have a mobile application in which you can configure several aspects of the IoT. But then sometimes you also have, like, I don't know, a distribution of IoT devices, as happens with the Philips Hue light bulbs, and then you have a centralizer which controls how the light bulbs work. So the architectures in an IoT system are really huge, and a big part when testing them is to understand how they are made and what do you actually need to test, okay? Which leads us to the 5 IoT pen testing categories, okay? The way, the methodology and in the way that I have divided an IoT pen test is in these 5 categories. So essentially you have the hardware, which would be the physical security of the controller, but also have they left the built-in interfaces that can be accessed by an attacker? Do they have, like some IoT devices have all the information stored in a micro SD card? So is the firmware there? Can I extract the firmware and then do what I want with it? Then we have, of course, the web and API category, the mobile application category, and the radio communication ones. Hardware and firmware you will always have, but the other 3 are optional and will depend on the architecture that you find. The key here and the concept that must, I think the goal is to encourage people to lose like the fear of pen testing IoT devices because they are too complex, is to split the architecture in something that that they can understand, because Weapon API, there's a lot of documentation on how to pen test. Mobile applications is the same. Firmware, there's also some documentation, and apply these atomistic categories to an IoT pen test as a whole. What I did during the research that ended up developing the methodology, and let me do a small update here. The methodology is going to be public. It is not public at the moment. I want to do it, but I'm waiting for the moment to update it with the last information that we've get from doing different pen tests in the company where I'm working from. But yeah, at some point it will be public. If anyone has a doubt about it, you can drop me an email or whatever, and I'll be happy to answer. How it's going to work during the following slides is we're going to see the state of the art of each of these categories, and then we're going to see which work was done to understand actually how to test them and the mapping of the test that a pen tester can do for each category. So the state of the art of hardware pen testing was pretty limited. If you go and search online for hardware security, hardware pen testing, hardware offensive security, you'll see that the options are very, very limited. There is one page, which is called IoT Pen Testing Guide, which has a lot of interesting information, but limited. But they had key concepts as the FCCID identification that allows you to get an understanding on how the IoT devices are made. And there was also some articles from FireEye that essentially explain that the first part when trying to break a hardware is to research the device, identify the components, know how it works, which parts does it have, and then try to dump the flash, and from there extract and analyze the firmware. So what I did in this category was first try the FCCID identification that I told you. So the FCCID, it's the Federal Communications Commission from the United States. Essentially, it gives an identification number to each device that has to be sold to the public, and then they put some of the information of the test that they do to guarantee that the device works in the intended frequency and that it has acceptable values according to the law. And all those documents are uploaded online. But also I try to find user manuals, data sheets, change logs. And for example, here you can see the example of an Amazon Echo. I took the FCCID, as you can see here. And then by searching for fixing guides, you can see exactly which components it is using. So imagine you want to dump the flash memory of the Amazon Echo, then you know exactly where it is sitting. You can then spin up the documentation of this specific chip and see where is the information stored. It's not a simple process, okay? So soldering, it's another difficult part when you want to retrieve this information, but at least you know where to start, okay? And what you can see in the FCCID page, is essentially the disassembly and the model and the frequencies and the protocols that the device accepts. So for example, if you go to this web page, which is publicly available, you're going to see an Amazon Echo teared up into pieces to understand how it actually works. And we jump to the firmware and the state of the art of the firmware. And here we have, throughout the presentation, we're going to see the different tools that the WASP offers. So here we have the firmware security testing methodology, which explains in detail how to first understand how the firmware is working, how to extract it, and then how to analyze it. And also there were some articles explaining why BeamWalk, and maybe if there are some of you who play CTFs now and then, you're going to know what BeamWalk is used for. So it's a tool that essentially parses a file and keeps identifying the magic numbers. And then once he knows that the file has, 10 smaller files inside, it extracts them in a folder for you to review. So essentially it's like a decompressor for file formats which are not known. And what we have in the FSTM guide, it's so they have composed it in 9 stages, and they start by gathering information, and they explain the different methods of obtaining the firmware, how you can analyze it, how to extract it, and then how to analyze the file system. In the file system is where you're going to find the gold. It's when you're going to find the credentials, the hard-coded credentials, and all that information that the WASP was warning us about, okay? So if you want to get to know if there are insecure network services, if there are weak guessable or hard-coded passwords, then you're going to find that in the file system, which most of the times is something similar to Linux. So what I did in this category was to first I bought a baby IP cam, which was known to be vulnerable. In this case, as you can see in the picture, it was exposing the UART ports. So I soldered it myself. I soldered the connection with the UART to USB interface, and then I was able to interact directly with the IP baby cam. What is also important to know is that most of the times you are banging your head into the wall to extract the firmware from the flash memory chip, but some of the manufacturers actually release it online. So, for example, what you can see in these images here is the firmware for a well-known router from TP-Link. And if you get this firmware, then you can unpack it. You see the binary, then you can run beanwalk on it, and you're going to see the different files that it's using. The goal when you get this firmware is to be able to emulate it. So you'll have to understand in which architecture it is running, and then using QEMU or the appropriate tools, you can emulate it in your machine and interact with it as if it were a live device. And with that said, we go to the third category, which is web and API. And here WASP has us covered, so we have all the documentation that we want, all the guides on how to test applications, which tests should be conducted. We have the WASP Top 10 for application security. Likewise, we have the WASP Top 10 for API security. So lots of good information, but although you can find any of the well-known web vulnerabilities in an IoT device, there are some specific vulnerabilities which are more relevant in IoT devices, which are the ones we're going to discuss now. And I'm going to explain why. So these vulnerabilities are injection vulnerabilities, buffer overflow, and diffing vulnerabilities. The reason why these vulnerabilities are more relevant in IoT devices is that, for example, with injection vulnerabilities, if the website is hosted directly by the IoT device and you find a way to execute code as in a remote code execution, then you're already touching the device. So you don't have any additional security measure that is going to impact you. Maybe you can have users as a /data that will restrict you from jumping to the root. But then again, we've talked about how IoT devices are hardly updated. So probably it will be easier for you to find an exploit that allows you to escalate privileges. Likewise, if you find a buffer overflow, the most likely scenario is that memory protection techniques like DEP or ASLR are disabled. The reason for this is that you have to think how much it costs an IoT device. So if you have an IoT device that costs €5, and they have to build the device, build the web page, build the mobile application, this stuff is expensive. So sometimes the usability versus security wins the usability, and then they decide to disable all these memory protections that we are used to in Linux services and in Linux operating systems to make the device run smoother. And last but not least important, diffing vulnerabilities. Diffing vulnerabilities have gained a lot of popularity. Well, they have always been popular, but for example, this last month, I think we saw maybe some of you can recall the Confluence vulnerability, where there was a patch that was released, and researchers, when they saw that it was a critical security patch, they downloaded the patch, they reversed it, and they knew exactly what was the problem. And in a matter of days, they were able to develop an exploit, which started to be exploited in the wild in a matter of hours. With IoT devices, happens the same, with the idea that most IoT devices are never updated when they need to be updated. So now imagine that the security researchers gets your Amazon Echo device or gets your the IP cam that you have bought for your home, which was only €10 and seemed like the perfect deal, and they see that there is a remote code execution vulnerability, and the manufacturer releases a hot fix. If the secure update mechanism isn't there. If the devices are not updating automatically, then in a matter of days, this vulnerability will be exploited in the wild. What you can see in the screen, these two screenshots, are basically an academic dummy case to show the risk. So imagine that you have the old firmware where you get the variable in PHP, and then you do an eval to it. Eval has long been regarded as a vulnerable function, and is used in CTF for those of you who play. And now the manufacturer releases a new file, which essentially tries to sanitize the input. Okay, this is what you need. So what an attacker will do is they'll know that the new file has a security fix, but they don't know where it is. They'll just do a diff, and they'll know exactly where the injection point is. They're going to then enumerate devices which they know have not been patched, usually because there's the version number in the footer of the page, or well, a lot of different measures, and they'll have remote code execution if that's the case. With that said, we go to the fourth category, which is mobile applications. And again, OWASP has us covered, okay? We have the OWASP 10, so we know which are the things that we want to be secure for. And we know how to test for these vulnerabilities because we have the mobile security testing guide. What I did during the research here was, first of all, to understand how I'm not a mobile pen tester, but yes, understand how the process of pen testing a mobile application works, how you can reverse it, how you can extract the Java files, and how you can understand how the application works from there. One tool that is used to reverse applications APK is its APK tool. And essentially, when reviewing some of the cheap mobile applications for IoT devices, there was one which essentially was doing what, and I'm going to the beginning again. So what the OWASP is warning us about. So weak, guessable, or hard-coded passwords. Okay. So what they were doing is, if the password has not been set, then the password will be no password. So then if you just build your payload, then you're going to be able to interact with the device as if you were the owner of it. So again, we're not looking for that specific book that is super complex and that needs 2 months of research to find. We're looking about bad practices from the IoT manufacturing companies that could leave organizations at risk. And we go to the final category, which is the radio communication one. So there were some articles in radio communications. There are some articles on this and I've seen lately some extra ones which have appeared on how to test IoT devices for the Bluetooth Low Energy vulnerabilities. And also there is a really good talk from Black Hat USA 2015 that explains how Zigbee works, where are its vulnerabilities, how you can exploit them, how in certain scenarios you can jam the communication to force a certain key to be sent, and you can intercept it, and then you can take over the devices. So all these ideas, and well, here it was the first time I saw Zigbee and Bluetooth Low Energy. So I first tried to understand how they work. They are really specific protocols. You have to think like they are like HTTP or TCP, like you learn them in college or on your own, but you have to study them and you need to understand how they work before you're able to craft requests. And then using Bluetooth Low Energy sniffer, I was able to intercept the request from a lightning bulb, which was vulnerable. And I was able to change the color of the bulb using the computer. Okay. So before finishing the talk, I wanted to present 2 real world case scenarios, which we have tested in the company where I'm currently working. Explain which have been the takeaways that that we have seen from doing these pen tests, and where we think are the risks. Okay. So first, I've drawn a little bit which was the architecture of the IoT system that we're going to pen test. So as you can see, so for you to understand, these were like smart lightning panels, which are placed on the factories in the rooftop. So depending on the light that comes from inside, they can change the amount of light that they are emitting, and also depending on the number of sound and the footsteps that they hear, they can change also the quantity of light that they need. The architecture that the company providing this service was using is they had an on-site web appliance, which was a Linux server. Then they would connect directly to our internal network switch. They would place their network gateways there, and each network gateway which would communicate with 20 to 50 lightning panels. So we had several network gateways. So the first thing that we need to understand was what needed testing. Okay, and in this case, you can see it is pretty clear. So we had the web appliance server configuration. So it was an Ubuntu machine, a really updated one. We had the web application. We had the different gateways. We have the Zigbee connection per se, and we had the lightning panels and the physical security of those panels. When there is a gateway, usually the logic of the application sits in the gateway, and the Zigbee doesn't have, the lightning panel or the end IoT device doesn't have much intelligence, and all the magic, to say it in some way, happens on the gateway, okay? So which were the high-level findings of this pen test? So when we started like scrubbing the surface and saying what was happening and what was there, we saw that the system was using an outdated Linux machine. So it had an SSH open for administrative purposes, and it exposed several additional outdated services like Apache 2. So imagine one day this SSH key or SSH password gets lost, then in a second, all the bad guys can access, I don't know, several IoT systems in the world. Also, the Linux machine was not updated, was provided as is. When checking the web appliance, HTTPS, which is an internal requirement that we have at the company, was not being used. There was no password complexity on the web page. Default credentials were being used both in the SSH service, as I have explained, and in the web appliance. The light engines were also exposing some debugging interfaces, and they had, well, several additional web vulnerabilities. So you're going to wonder, where are the radio communication and hardware vulnerabilities? And one of the conclusions of the pen test and of the work that we have been doing internally is that usually the company commercializing a service like this Smart Lightning, for example, builds the web page, can build the mobile application if there's one, builds the server where everything is going to happen, but doesn't build the Zigbee modules. Because for specific network modules, it happens the same with the GSM modules that mobile phones have. There are only few suppliers in the world that produce them, and they make sure that the chips are working as expected and that are implementing the radio communications protocols as they are supposed to. Another thing that can happen is that sometimes companies will tweak some of the configuration, and there are occasions where you can find some security measures off that can put the system at risk. Okay. The second scenario that we have been tested is the connected coolers. Okay, so essentially there is a fridge which has a cam and can take photos of if the bottles in the fridge have been emptied or not, and if the fridge needs a refill. And this system had an iOS application, but it also had a web appliance that was built on top on Azure IoT, which in turn communicated with Salesforce. So you see, again, a pretty complex architecture where you need to test different things in order to give some assurance on the whole system. No? And the things that needed testing here were the web appliance, the iOS application, the Bluetooth Low Energy connection, and the controller of the fridge, and also the integration with Salesforce. So which were, again, the findings, and the idea repeats, okay? Several web vulnerabilities were found, okay? So we had XSS, password related ones, session management, and also several mobile application vulnerabilities. But on the other hand, the device was really well protected. So it was following one of OWASP's IoT ISVS recommendation, as you can see on the screen. So all the contents of the controller were filled with this type of glue, which was in turn covered in a black with black painting, and it was impossible to know which chips were working, if you could extract something from there, if there was a debugging interface that you could plug into. It was really difficult to do. We tried to pry it open, but yeah, it was really secured. And also the Bluetooth Low Energy connection that the controller was using authentication. So first, the mobile application would connect to the cloud and retrieve some type of credentials. Then the iOS application would do a connection to the freight using Bluetooth Low Energy, which would in turn check with the online application if it was allowed to access. So this made the Bluetooth Low Energy also non-straightforward. We tried to do a Python script that could interact with it and try to bypass it, but yeah, it was a lot of time, and we gave it a green check. Again, which are the conclusions of this pen test that we did to the connected coolers? That the things that are sold at scale. So, for example, I imagine that the company that sells this controller is selling millions of them, are well protected. They know that they have an IP that they want to protect, and they do it really well. But then, where you can find more opportunities or more vulnerabilities in the web application and mobile application, where it's something that is being custom made and can be vulnerable. And we have arrived to the conclusions. So if you have followed the talk, I hope I have been able to convince you that although sometimes we might lack time and knowledge of a specific IoT device, there are always tests which can and should be done to make sure OWASP's IoT top 10 vulnerabilities are avoided. It is not only limited to the pen testing effort. So again, if you go back to the beginning, I think it's really important to have a really good third-party security assessment where the provider explains which security measures they have used for the IoT device. And also, if you are the one onboarding the IoT devices, use a platform that makes it easy for you. So that allows you to see which devices are communicating, why you have some of them which are offline, why you have an outbound connection to a service that might be dangerous, etc., etc. And yeah, radio communications modules are usually out-of-the-box devices that are acquired from a limited number of suppliers and are usually well protected. So I think there has to be specific research there, and it's not something that the companies can do. And that if you want to try all these IoT-specific communication protocols, you're going to need a specific equipment, but there's plenty of information online. Thank you very much for listening to me. If you have any questions, you can drop me an email, you can find me on Twitter, or you can ask here.
Awesome. Thank you, Arnau, for the presentation.
Thanks,
that was
Arnau.
great. I'm not sure if we've got any questions through more Slack, but I do have one. So I wanted to ask you, when you find those vulnerabilities on the devices, right, and you, I guess, you report that back to the vendor. So how that process is and the experience, right? Because sometimes the vendors, they don't take
it's
in the right way.
Yeah, it's super difficult. So when they have a vulnerability, getting them to fix it is hard. For the first scenario that I've presented, the one of the Lightning systems, what they said is, oh yeah, well, because someone told us that you wanted the internal Linux server option, but we also have a cloud solution which is well protected and has been tested. So you should probably just switch. And the company is like, okay, but we have just purchased the old system, so why are you telling this now? And yes, if you find stuff in the mobile and web application, usually it's easier for them to find. If you find a debug interface, or for example, in the connected cooler part, we found some credentials which were always being sent to the mobile application, fixing things which are in the skeleton of the application. It's really difficult for them, and yeah, it's a difficult process, but we try.
Well, at least you haven't been prosecuted, right? As yet.
Yeah.
Cool.
Did you manage to put some mitigation in place for those cases, or some?
Yeah, of course. So for example, some of the things that we reported and we said, so there are things that companies can refuse to do. For example, so when we found the Linux machine, which had SSH, this SSH service, which was always open with an outdated machine, and we said we don't want that there. So we have a level of security in the company that we try to maintain across all our assets, and you're breaching that security. They say, yes, we're going to do a small update and we're going to ship it, even if it's just for you, because they understand that it's something unacceptable. If you find stuff that is like, well, that is a vulnerability, but the exploitation is not so straightforward, then yeah, it's more difficult for them to fix it. Yeah, it's the same idea.
Okay, I mean, in those cases, I mean, I guess like
internally. You mean in the company internally? If we do,
yes.
Yeah. So, for example, what we do, and I think this is a work that other companies have to start doing, is in our standard we define the things that we want to know for sure. For example, things that I believe not the majority of companies have, like a good asset inventory, knowing which versions are running on the devices, where are the devices, because most of the people don't know where the IoT devices are placed. So we try to do some of that stuff internally, having, yes, like tracking files and having a list of the suppliers that we have that have put services in our network. As we would do, for example, with the VPN. No? So VPNs in internal networks has always been a thing, but nowadays they are trying to reduce it. But without the help of the supplier, there's only so much a company can make. But yes, we try to do our best.
Thanks.
Brilliant. Now, so thanks so much for your presentation. As said, so it's great to see local talent presenting in this conference. And I hope to see you again, hopefully face-to-face on the next conference. And yeah, all the best. Thanks for your time.
Yes, thanks a lot. Thank you.